particularly graph. We just use graphs as an example and do it. So let us assume that let script G be a set of graphs. It could be a category of graphs. That would be the specialty. This could be metric spaces or groups. So we are concentrating on graphs. I don't say focusing because I don't think I can focus. I don't know. This is the name, but this name doesn't focus. Okay. Set of graphs, and now we cannot use because we're using X for graphs, we can't use X for sets. We use omega. Any set. I'm going to define the weaker version first, and then we go to the stronger version. So the set of graphs, and then any set with an equivalence relation on it. Equivalence relation. This on it. What is a graph invariant? Graph invariant is a mapping from G to omega, so that isomorphic graphs have the images equivalent to each other. See, this is the weaker version of most general definition of graph invariant. So, if F is a mapping from this set to itself, it is not a mapping from its member. Okay. This contains graphs in the current case, such that if X, Y are members of G, and if X is a member of G, that's enough, then this omega. And X is isomorphic to Y, then Fx is equivalent to Fy. This the mapping is from the set of graphs to this any given set. And this set has an equivalence relation on it. So the images in images are equivalent to each other. This is the weaker version of more broad general rule. Then we call F graph invariant. This mapping F is called a graph invariant. I would like to ask you now to prepare examples of graph invariants and group invariants, the vector space invariants, the metric space invariants. For
it looks like distance preserving.
It looks like isomorphic graphs are mapped onto isomorphic objects are mapped onto equivalent objects. This is not like distance preserving. Of course, the
order and size of the graph.
yes, order and size. Example. Thank you. This is let X be a graph in G. I'm very happy with the Muhammad. Then this is the order. This order means that it's a cardinality of this set. And this size is also. Size I usually use W. Here the W is actually quite handy, and I'm not overusing something like functional analysis, where the one bar is enough, but you always have to put two bars. Sorry, they're not here. I can probably insult them. This is equal to the cardinality of.
Yes.
These two are graph invariants. What is omega in this case? What is that set omega in this case? Z, the ring of integers. And what is the equivalence relation now? Equality.
Yes.
So this extreme special case. It's in the tip of the iceberg. Any other graph invariants you can think about? We're going to define even this rigorously today. Chromatic number, connectivity number.
Yes.
Let us list it. They are all not changed under isomorphism. Connectivity number. These are still integers. Covering number. Independent number. Maximum matching size. If you cannot understand, please stop. And these are all we are sweeping through the whole country, because this is we are listing most of graph theory already, most of finite graph theory. Now these are all integers. These all belong to Z. So Z is our omega. And the idea. Equivalence relation is actually equality. Even if you include degree sequences, if you have two graphs which are isomorphic, then the degree sequence listed in non-increasing order or another order, they are equal sequences. So now we have a sequence equal, still equality, but now the degree sequences is not a numerical invariant. It's omega is a set of sequences. It could be even small LP. Small LP is a sequence space. More, we need more. Muhammad, give me a non-numerical invariant, which we were expecting when we were asking this question, but she didn't even know the degree, order, size, and so on.
Connectivity.
Connectivity is number of integer, but
Right.
connectedness is yes.
Yes.
Connectedness. Now, in this case, what is omega? You have to really give me omega as well. We are already, omega is probably 0,1, I think, in this case. And we still have equality. We still don't have a non-equality equivalence relation. Let me ask Muhammad, give me a non-numerical invariant where the omega is set and we don't have the equivalence relation is not just equality. And there are many, many of them actually. They are the most interesting invariants. Give me one example.
I cannot remember at the moment.
Remember, you don't need to remember, you need to think now. So,
It is divisibility graph.
divisibility graph is what invariance we have correct. Divisibility graph is you mean divisibility graph is the omega?
Yeah.
And what is your graph here now?
And equation is divisibility.
That is, if you take that as omega, the graph is, no, it doesn't work. Let me give you one of my favorite, which I really want, if you go for interview and if this question is asked, you should really give that example as number one. For any graph, the automorphism group is a group, right?
Yes.
If two graphs are isomorphic, then their automorphism group is isomorphic, which is not necessarily equal. So it's it's not necessarily equality, it's an equivalence relation called isomorphism. So odd G, odd X.
Yes.
If you have odd X already, this is a non-numerical invariant. Of course, omega is now groups, set of groups or category of groups. Non-numerical invariant, and this equivalence relation in omega is not necessarily equality. As soon as you have this, you have all sorts of similar things, like endomorphism monoid. Endomorphism monoid is also a non-numerical invariance, and if two graphs are isomorphic, then the endomorphism monoid is also monoid isomorphic. Spaces defined on graphs, vector spaces. Have you seen any of these examples in your graph here? Defined on graphs. For example, the space is called, one space is called cycle space, another space is called co-cycle space. There's another space which is the intersection of the cycle space and the co-cycle space called bicycle space. These are all cycle spaces, cycle space. This is a vector space, co-cycle space, and these are non-numerical graph invariants, examples of non-numerical graph. Now we want to look at this definition again. Now I don't have right talk. What does this definition say? This definition says that F is a mapping from G to G. And you have a mapping from, F is a mapping from G to omega. And you have an isomorphism here, phi, from G to G. This diagram commutes. Let me put the F on the others. So the F is a graph invariant if this diagram is commutative. Not only so, you can actually have a diagram with forward rows. If we say this in terms of isomorphism, so if phi is any isomorphism, then what are we saying? We are saying that this F phi x is equal to fx. Is that right? For any graph in G, isomorphic objects and the original objects have the same image in omega. Now this is true for every x. So we can actually, if such things are happening, we can say that f phi is equal to f for map in terms of the map, right? Which means there's another name for it. Now, every automorphism is a right identity element. One condition, two conditions, three conditions, four conditions. Every isomorphism is right This is the definition of the invariant with respect to F. Because F is an invariant if every identity is the right identity for F. Another way of writing this is phi F of is F. This works for every isomorphism. Okay. I think we have now covered the general concept of transformation graphs. Of a transformation graph. I omitted one example. And then we rigorously define what is meant by graph invariant, which can be moved on to invariant of other mathematical objects such as matrix spaces or groups or vector spaces or Euclidean spaces. Right? Of course, for undergrad people, I think this is becoming too abstract. But I think for our entrance students, this is all seen, right? You have seen this kind of thing in other courses. But it's only coming from graph theory, which is a little surprising because in graph theory, you don't have this kind of things inside the text or people who are lecturing. Now two things we have done very rigorously. One is called transformation graphs. The other one is called graph invariants. There is another example which I will just talk over. So for this example is for matrix spaces. If X is a matrix space, then the invariance is invariance under this mapping is replaced by isometry. So if this every isometry is the right identity, then this F is invariant. But from matrix space to a set, we're not even talking about from matrix space to some number rings or something. And if it is graphs, then that is isomorphism. And if it is vector spaces, then it is linear endomorphisms, linear homomorphisms, linear mappings. And if it is Euclidean spaces, then we have orthogonal transformations, this phi. So every orthogonal transformation is the right identity. Then this last one, second last one I prefer because we don't need to talk too much. Is that every orthogonal mapping is the right identity, then that mapping which sits on the left is called an invariant of Euclidean spaces. Are we losing someone? What is the time now? Because I don't have any more. There are more, but it is a repetition. Any discussions? Any questions or discussions? There are also integral invariants for graphs. For example, the determinant of the adjacency matrix is invariant. That's additive. A is the adjacency matrix. And determinant, this is an integer. As soon as you have this, then you have a matrix, so you can actually calculate its spectra. Spectra is another example of an invariant, but it is no longer just numerical. Spectra can be several set of numbers. And if you calculate the Laplacian spectra, then it is another example of a graph invariance. I wish if anybody is in this room in the future, maybe 20 years later, studying some of these invariants which are not integer invariants, then I would be very happy today. Because I can't say then I will be happy, because then I don't know really. What is the time now? Few minutes, 30 minutes. So let us discuss any questions. This is quite abstract, except this two examples. Even this easy example gives us a question here. This question, if anybody is interested, probably we can work on it. So not necessarily cubic graphs or any other class of graphs, you define a well-defined transformation and then see if of the same order the graph is connected, and if on all order the graph is connected or not. That kind of question you can ask and answer here. And then those will be, I'm sure that if you have any result in here, you can get it into the combinatorics journals, which are really highly respected by my colleagues. But I usually respect the Society's journal better since 2012. Society means Canadian Mathematics Society, American Mathematics Society. They have several journals. The Society journals have referees for subjects which you are doing. But the combinatorics journals, if you submit the metric space result, although it contains graphs inside, they can't refer it. So they will tell you politely that we are not interested in your paper, meaning that our journal scope is not covering this paper and so on. But the society journals, if you have a geometry result or algebra result, then if you submit, they definitely have people who can refer it. So you should also try to respect the society journals more. Subject journals are top, of course. Because subject journal means if you are in algebraic geometry, it's algebraic geometry journal I'm talking about. But the subject journals are highest on the list. But the society journals they will always have referees. It is a very pity that if you submit a good paper and you don't have a referee to refer it, and then they will give you a very polite reason to reject it. Of course, I didn't see this kind of experience. I had one experience, one paper, which was a calculation of my student, calculation of isometric groups of a certain metric space. Sent to this journal, said no, we don't accept this paper. Sent to just that journal, he said he was the submitting author. And we don't want this, this is out of our scope. So he submitted 3 times, I think. The first time he paid and published. And I don't like paid journals. He lied to me. He said, no, it's not a paid journal. And then later on I asked the journal. He said, no, this is a paid journal. But I can't be angry with him because he is a very good student. So if anybody is interested in transformation graphs, even for divisibility, it would be very interesting to work on. You can actually program Python and then work till from 1 to 1 million in a very short time. And then you will start seeing some structure in there. It would be very interesting. I never did that because even for these 20 vertices, 21 vertices, I didn't Python it. Please discuss any questions, any comments. Tomorrow we are going to define geometric sets, not on Wednesday. And then after that it's going to be very difficult, I think. After the basic part is over, I'm not going to include those as examinable content. So you are going to sit exams in this, right, which was required. So only the basic parts will be covered by exam or manual test. After the geometric sets are defined, it is 3-4 papers I'm going to introduce. That results in 3-4 papers. So those will be quite involved, and maybe I can't go carry through, but we'll see. We just work like this, and when I'm stuck, it's fine. In my own paper. actually stuck in my memory, yes. There was an error actually, but it didn't influence the result. Any discussions or questions? So the scope for exam is up to the end of the geometry set, the next batch of slides. After that, it will be topic introduction, which cannot be easily examined. But when there is some question which is easy enough to come as an exam, I will point it out for you. Exam scope must be transparent to the student because we're not dealing with enemies. And it is right to actually tell the scope. Even with telling the scope, it is also, there's a risk of failure.
Yes.
Yes. Any questions? Any questions, ladies? Okay, then we will be fine. Right? We are early today. 24 minutes left. Or would you like me to continue on to the geometry sets?
No, we're going to this.
I can't. Okay, then we will conclude the lecture today. Geometric sets we will do it on Wednesday.
Yeah.